Hi everyone, it's Miss R Squares Up with Math. Today we are squaring up with scientific notation. So, scientific notation. Scientific notation is numbers written using the powers of 10. What does that look like? Let me show you. Now, if I write something like this, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 6, 10 to the power of 7. Did I just do that? Yes, I did. Do I have your attention now? I hope I do. Now, this is 10 to the power of 2, 3, 4, blah, 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 blah. It doesn't matter. That to the power of is another way of saying exponent. Now, what is an exponent? Exponent, it shows repeated math. Specifically, repeated multiplication. What does that mean? For example, let's break down 10 to the power of 2. 10 to the power of 2 translates to 10 times 10. Why? Why do we write it like that? It's because in math, it's easier to write just one little term than two. It's easier to condense it that way. Now, this 2 is called an exponent. This 10 is called the base. Now this 2 is telling you how many times does 10 occur? 2. Do we have 2 tens? 1, 2. Yes, we do. Now, let's say I change it up. Let's say I do 10 to the power of 3. It's asking me how many tens occur? 3. 10, 10, and 10. Okay, but I'm missing something. The exponent is supposed to tell me repeated, what was it? Multiplication. So, multiply, multiply. I gotta remember to put that. Again, so on. 10 to the power of 4. How many tens occur? 4. So 10, 10, 10, and another 10. Is that 4? Let's see. 1, 2, 3, 4. Okay, I have my 4 tens. What am I missing? Let's see. Exponents means repeated math? No. Repeated multiplication. So, missing my multiplication sign. So that is what that means. So 10 to the power of 2, same thing as in 10 to exponent 2, doesn't matter. It's all saying the same thing. It's all telling you that 10 occurs twice, you're multiplying them. 10 to the power of 3, it's telling you there's 3 tens, you're multiplying each of them. 10 to the power of 4, 4 tens, you're multiplying each and every one. So you go step by step, 10 times 10. Then whatever you get, times 10. Then whatever you get, times 10. And so on and so on. So, with that being said, scientific notation is using this for the base of the equation. I'm going to show you an example of scientific notation and what it looks like. This is scientific notation. That is scientific notation. That's it. Just that little, right there. That little equation right there. Now, do you notice something? I do. It has 10 to the power of 5. That defines scientific notation. Scientific notation is defined by that 10 to the power of something. That is what you need for scientific notation. Because again, scientific notation is numbers written using powers of 10. Now, what if I told you that this actually translates to this? A little bit confusing, right? It's okay. All they're doing in math is they're taking a huge number and they're like, let's make this a little bit harder kind of thing. But no, let's make this a little bit easier, quotations, in a standpoint to look at it in, I don't know, let's say an equation, a math problem, or anything like that. Instead of reading 450,000, I'm going to read, 4.5 times 10 to the 5th power. Now, what I'm going to show you is I'm going to show you how they got this to this and backwards. I'm going to show you how to get this to this. So let's work from 450,000. Let's work from there. Now, with scientific notation, you are breaking it down. Scientific notation, you have to make it look like this. A number, decimal, a number, times 10, always has to be that, to an exponent. Exponent, remember, also means to the power of. Cool. So, this number right here, we always want it to be a number other than 0. We do not want that to be 0. We want that to be 1, 2, 3, 4, 5, 6. I don't care. It does not need to be 0. This number can be 0, but this number cannot. Okay. With that being said, I am going to move my decimal. At the back of every whole number is a decimal. So, do you see a decimal here? No, I see a comma. That does not count. Let's see. At the back of every whole number is what? A decimal. So my decimal is going to be right here. To diverge off a little bit with that, decimals. If I give you 2.5, where's my decimal? Correct, right here. If I give you 11.5, where's my decimal? Correct, right here. If I give you 13, where's my decimal? Let's think about that one. Do we see a decimal? No. So just know, at the back of every whole number, there's a decimal. We don't see it. We don't see it because why would we keep the decimal there? We don't need to see it. Think of money. $13. Looks like that, right? But do we write this every time we want to write $13? No, we write this. Because what's the point of seeing a decimal and some zeros? But just know, at the back of every whole number is a decimal. Okay? So with that being said, I am going to move this decimal over so I can condense it. I want it, again, to be a number other than 0 in whatever number or 0 here. So, in order to get a number other than 0 in the front, let's see how many times I'm going to move my decimal. I'm going to move it 1, 2, 3, 4. Sorry. 1, 2, 3, 4. Now, do we want it to be 45? No, we want this to be the smallest number possible without it being 0 in the front. So, I'm going to move it over again. 5th time. Now, our new number is what? If we move this decimal from here to here, our new number is 4.5. Now, with scientific notation, this always stays the same. This right here. Now, the exponent will change, but the times 10 will stay the same every single time. Every single time. Now, with that being said, let me put my times 10. Now, I need to figure out my exponent. Let's think. My exponent. Where would I get an exponent from? Well, I'll tell you. The exponent will be how many times you move the decimal. So let's count. We moved it once here. Okay. We moved it again here. Okay. Again here. Again here. And again here. So, how many times did we move the decimal? 5 times. So that will be our exponent. It looks hard, but it's actually extremely easy. We're going to do another one. Let's say I give you 35,000. Now, we have 35,000, right? I want to get it to look like scientific notation. Has to look like a number, decimal a number, times 10, and then an exponent. Remember, this number cannot be 0. We don't want it to be 0. This number can, but this number can't. Cool. With that being said, let me rewrite this so I can get it some more space. And I'll give you a moment. I suggest pausing the video and try it yourself real quick. Cool. If you did not pause the video, let's get going. Now, I'm going to show you again. At the back of every whole number is what? A decimal. Yes. Cool. Now, I have my decimal there. Now, I want it to get to the smallest number possible without 0 being the front. So, I'm going to assume that this 3 is going to be the front loader. And I'm going to assume that this 5 is going to be the back loader. front loader, back loader. So with that being said, I'm going to move my decimal right here. I want to move my decimal right there. So I'm going to count how many times I have to move my decimal to be right here. So let's count. 1, 2, 3, 4. Moved it 4 times. So my new decimal is right there. So my new number is 3.5. Now I write my times 10 like every single scientific notation equation will have. Now I'm trying to find my exponent. What was my exponent again? Right, it's the amount of times I move my decimal. How many times do I move my decimal? Let's count. 1, 2, 3, 4. I move my decimal 4 times. So my exponent is going to be 4. That's it. That's all it is. Now, I am going to turn my page, and I'm going to show you another way. This one may be a little bit harder for you, but I'm going to show you what a negative exponent could look like, what a negative scientific notation could look like. Now, I'm going to write a small note that you need to remember. Okay, so positive exponent, number big. That's it. Negative exponent, number small. Now, I wrote it in those terms because that's the easiest to, speaking like a caveman, basically. If it's easy to remember, positive exponent, number big. Negative exponent, number small. Easy. Easy in my eyes. Could be easy in yours, but just think of it like that. Now, what I mean by that, with our other one that we just did, I'll go back. Do you see something? This is a positive exponent. Why? There's no negative there. There is no negative there. So that means it's positive. Now, if it had a negative, that would be a negative exponent. But there's no negative, so that means positive. So, like I said, positive exponent, number big. Was our number big? Yes, it was. Now, negative exponent says number small. Let me show you what that looked like. If I tell you to get scientific notation of 0.0072, this is number small, meaning our exponent is going to be negative. Why? I'm going to show you why. With our big number, we move the decimal from the right side to the left. From here to the left. Now, do you see something here? Which way do you think we have to move our decimal? Left or right? Left being this way. Right being this way. I'll give you a second. If you said right, you are right. So, if you have to move your decimal from left to right, your number, your original number, is going to be small. If you had to do that, that means this number is small. Is this number small? Yes. That means if you had to do this, your exponent is going to be negative. So, with that being said, I wanted to debrief you on that. I'm going to go back to our positive exponent really quickly, just to touch base on how to do it opposite. When I say opposite, I mean if I give you 2.5 times 10 to the power of 3, I'm going to show you really quickly how to get our number, our original number. Now, the exponent is what? Negative or positive? Positive, exactly. So that means, let's see, positive exponent means number big. So our number is going to be big. Let me rewrite 2.5. Now, if I move the decimal this way and add zeros this way, my number is going to get smaller. Positive exponent, number big. So I have to move my decimal this way. And then add zeros this way for number big. So let's do that. Now, I have 2.5. It's telling me how many times did I move my decimal. Remember, up here, I got the exponent because I counted how many times I originally moved the decimal. So, if I counted how many times I originally moved the decimal up here, I originally moved the decimal 3 times, right? To get 2.5. Now, all I got to do is move it back. So, we're going to move it back once, twice, add a 0, 3 times, add another 0. Okay, so that means our original number was 2,500. Let's double check our work. Let's say our original decimal was right here. Let's count how many times we have to move it to get 2.5. 1, 2, 3. Does that make sense? Yes, it does. So, we know our original number was 2,500. Now, flipping back, let's go to negative exponent. Now, if I give you a negative exponent and we want to get scientific notation, it's going to look like this. Number, decimal, number, times 10. Same thing. Exponent, but key thing, negative. It is going to be negative because we're moving it to the right. We are moving the decimal to the right. So, our exponent is going to be negative. Cool. So, with that being said, let's move our decimal so that we get a number other than 0 and then another number. Okay, so I'm going to assume that I'm going to move it in between here. It makes the most sense. It makes the most sense. Because if I move it back here, do I want 72? No, that's too big. That's too big of a number. So I want to get the smallest number possible, which is 7.2. So with that being said, let's move our decimal to get that. It starts here. So I'm going to move it. 1, 2, 1, 2, 3 times. So my new number is 7.2. Now, remember scientific notation. Times 10. What's my exponent? How many times did I move it? Okay. 1, 2, 3. You can count how many times you move the decimal here, 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 or you can count how many times you have a swoop. Either or. Now, I know I have 3 swoops, so I moved the decimal 3 times. Now, I know my exponent is going to be 3. Wait a minute. I'm missing something. Negative exponent, number small. Is number small? Yes. So, negative exponent. Remember, if you have to move the decimal to the right, your original number, is going to be small. Now, with that being said, let's work it backwards. Let's do another one real quick, and then we'll work it backwards. How about that? Let's say I give you 0.00067. Did I do that again? Yes, I did. Do I have your attention? I hope I do. I hope I still do have your attention. I hope I do. Now, let's work this one. Now, again, I want to have a number other than 0 here, and then another number or 0. Doesn't matter. This one doesn't matter right here. This, if I could draw an arrow. Yeah, you get the gist. Now, I'm going to assume that it's going to be 6.7 because, again, I want a number other than 0 here, and then I want another number there, or 0. So, I'm going to move my decimal point until I get 6.7. So, let's do 1, 2, 3, 4. Now, my new number is 6.7. Remember, scientific notation, so times 10. Now, in order to get our exponent, we have to count how many times we move the decimal. How many times do we move the decimal? Once, twice, 3 times, 4 times. Meaning my exponent is going to be what? 4. Now, remember, which way did we go? Did we go left or did we go right? Is the number small or is the number big? You can ask yourselves these questions to know if it's going to be a positive or negative exponent. Our number is extremely small starting off. So, our exponent is going to be negative. Our exponent is going to be negative. Just remember that. Now, let's work backwards. Let's say I give you 3.2 times 10 to the power of negative, let's do 3. Now, again, always restart always start with taking it out. Do not try to work it from here. You don't have any space to work it from here. Rewrite your number. Rewrite your 3.2. Then work it out. So, how many times did we move the decimal from the original number to get this number? It's telling us 3 times. However, it has a negative there. That is key to knowing which way we go. If we move our decimal this way and add zeros this way, the number will get bigger. Now, positive exponent, number big. Negative exponent, number small. Now, we have a negative exponent, meaning we don't want to add zeros this way. We want to add zeros this way. Now, let's do that. I'm going to write my 3.2 over here so I give myself a little bit more space. Let's see. 1, 2, add 0, 3. So that's saying that our original number was 0.0032. Let's double check our work. Did we move the decimal 3 times to get that? Let's see. 1, 2, 3. So that means that would be 3.2. Meaning our original number was this. So we are correct. Our original number was 0.0032. This can be written as 0.0032 or 0.0032. I highly recommend doing it this way. This way makes the most sense. It makes it visually appealing. Visually makes the most sense. So let's do another real quick and then we'll end our video. Okay, let's do 2.3 times 10 to the negative, let's do 2. Negative 2 power. Now, again, bring my 2.3 down. Now, how many times did I move my decimal? 2 times. Is it negative? Yes. So if it's negative, I'm going to be adding zeros this way. I want the number to be small. Number small. So let's move my decimal 2 times like it tells me to do. 1, 2. So what it's saying is that my new number is going to be, my original number is going to be 0.023 was my original number. Let's double check our work. 1, 2. Did they move the decimal twice to get 2.3? Yes, they did. So that means this is our original number. This is our scientific notation of that original number. Now, if you have any troubles with understanding any of this that we went through today, it's okay. Just let me know. Communicate with me so I know if we need extra help, if we need to explain it maybe in a different light, in a different view, in a different way. And that was Squaring Up with Miss R. And today we squared up with scientific notation. Tomorrow we'll square up with something else. See you then.